Hello, thank you for tuning in to my video. I will discuss some of my graduate science research project in an accessible manner as a product of the Relate Summer Workshop on Science Communication. My name is Paul Chao, and I'm a student studying material science and engineering at the University of Michigan. Today, I'm excited to share my research with you that is at the forefront of studying materials formation and behavior using cutting-edge scientific techniques we currently have available. We have recently captured detailed data that allows us to visualize the growth of two metal crystals, shown here, which I'll explain more during the video. I hope you relate to the work I'm going to share and inspire your imagination into the natural world around us. Thank you in advance for your time and attention. Now let's get started watching two metal crystals grow together. So when I talk about two metal crystals growing together, there's been a variety of complex patterns I've observed in the aluminum to copper alloys. The left, it looks like an ordered layer of metals, and on the right, it appears to be a complex maze. Both of these patterns have been observed in the same alloy, and we will leverage new techniques to gain insight on how these patterns form in real time. But first, let me back up and discuss the crystal growth of something you might be more familiar with: ice. The ice cubes we find in our freezer, or here at Michigan, the snowflake falling from the sky during the winter, is an example of pure water in its solid phase. The snowflake can be captured on video in a laboratory setup with a controlled environment. Here you can see the beautiful symmetry of this crystal and the rapid increase in size in a beautiful symmetric pattern. The transformation from liquid water to solid ice occurs when the temperature drops below 0 degrees Celsius. We call this the freezing point of liquid water. If we heat ice above this temperature, it will melt and become liquid water. Now I hope this video piques some of your curiosity in the dynamic process of freezing, because the freezing point is important. In my research, I do something very similar to understand patterns formed as the metals can freeze. Now, water is a pure phase with a freezing temperature we're familiar with. Pure aluminum has a freezing point of 660 degrees Celsius. Pure aluminum to copper has a freezing point of 591 degrees Celsius. The freezing point of these pure phases is dictated by the elements themselves and are well known. Now, what happens when we talk about the freezing point of a metal mixture or alloy? Let me draw a line to connect the pure aluminum and pure aluminum to copper phase. We can describe aluminum as being entirely absent of copper, so zero atomic percent copper. We can similarly describe aluminum to copper as being 1/3 of it being composed of copper. Now, in between these pure phases, at exactly 17 atomic percent copper, the freezing point of the metal is at 548 degrees Celsius. This is lower than the freezing point of both pure phases and is the lowest temperature where the liquid can exist by itself. We call this the eutectic point. This word is derived from the Greek words eu, meaning well, and texis, meaning melting, because at 17 atomic percent copper, this alloy melts very well. And at this eutectic point, the aluminum and aluminum to copper will freeze and grow together simultaneously. Now, as an aside, I want to also note that similar to how we are able to create an ice cube using a mold, because the eutectic metals melt at a lower temperature than pure phases, they're often used and frozen into molds to make complex parts. So I alluded to the pattern of this eutectic earlier. Well, one of the patterns that can form are alternating sheets of aluminum and aluminum to copper. The width of these sheets are determined during the freezing process. I think of it as how fast the aluminum or copper atoms are able to move in the liquid to go to the solid phase while the solid is freezing. If the solid is freezing quickly, there isn't as much time for the atoms to move in the liquid to each of the phases, and as a result, the sheets will be thin. Now, these sheets are advantageous to engineer lightweight materials as an in situ composite with good mechanical properties like strength and toughness. This in situ composite can have a hard, stiff aluminum to copper phase embedded within a softer, more flexible aluminum phase to create a material with properties that is a combination of both materials. Understanding why these patterns form will allow engineers to control the patterning and design more advanced materials for society. Now, we sought to observe this dynamic process with advanced scientific instruments to watch this alternating sheet structure form. Now, how would I be able to watch it grow in real time, you might ask? Well, we watch the crystals grow by using high brightness X-rays. that can penetrate through these metals to reveal their internal structure. My schematic or illustration here is to present the setup in a general sense. If you're interested in learning more, there's an entire field of research dedicated to improving the instruments and techniques that enable our research, called microscopy. But back to the subject at hand. Going to the earlier example of snowflakes, scientists are able to watch a snowflake grow using a light microscope, which is essentially a magnifying glass, because the ice is transparent so the light can pass through it. And because X-rays penetrate pretty much all materials, except for lead, because it's a very heavy element, we can see through things that appear opaque, like metals, or even the human body. We use the high brightness X-rays generated from the Advanced Photon Source at Argonne National Lab near Chicago, Illinois to perform these experiments. The laboratory is a giant ring, which is so large it can encircle a Major League Baseball stadium. Within the ring are high energy electrons. These special electrons can be used to produce very, very bright X-rays, which we use to record in real time the metal crystals growing. The experiments I do use a furnace to control the temperature while we're recording what is happening. What's so cool about this experiment and the results I'm going to show you in the next slide is that we cleverly performed this experiment to collect both a video of the metal solidifying and the data to create a 3D render of the volume. The result is a 3D movie of the solidifying two-phase materials. Isn't that nuts? What I'm showing you here is the growth of the solid metal crystals in real time in our sample. This short video here is a real deal. It represents the two solid metal crystals growing together simultaneously into the liquid as it freezes. I had to digitally fuse together the experimental data to create this unique perspective on the pattern formation. The complex pattern is so mesmerizing and only possible by leveraging this powerful X-ray technique. And there's some really neat things about the results we collected. We've observed a structure that contains some sheets, some rods, and some sort of maze. We're detailing the results and discussion in a journal article, so look out for it later this year. But let me point out how small this volume is. It's roughly 10 times the size, 10 times smaller than the needle used to inject the COVID vaccines. To the right. Our ability to see things at this scale and at this speed is pretty exciting. And I think this is what makes my research project so unique. I hope this gives you a new perspective to appreciate how these solid materials can form. But before I finish, I want to share how this kind of research can be applied. For a long time now, complex automotive and aerospace parts have been made with an aluminum silicon alloy. This eutectic alloy has largely replaced its predecessor, heavy cast iron. It is very similar in strength, while being lighter, partially because of its in situ composite structure. This is an example of how research in these materials enables significantly lighter materials for engine blocks and other components powering our world today. I hope this inspires you to think about how scientists can design and engineer more complex materials in the future through the control of the metal pattern within. Thanks again for tuning in. Please feel free to reach out if you're interested in learning more. Thank you so much.